Hi and welcome to this presentation, which is about a GPU register file using static data compression. My name is Alexandra Anjard and my co-authors for this paper are Dr. Erik Sintun and Professor Per Stenström. GPUs offer a very high throughput through massive thread-level parallelism. And one key mechanism behind this high throughput is very fast context switching between threads, which is enabled by a very large register file. The key is that the state of all active threads are available in the register file during the entire execution of that thread. So that means that the register footprint, together with the register file size, limits the number of threads which is available, and thereby it also limits the thread-level parallelism of the system. If we look at register file trends for the past 6 NVIDIA microarchitectures, we can see that the total size of the register file has increased a lot the past 10 years. For example, the Fermi architecture, which was released in 2010, had a register file size of 2048 kilobytes, while the latest architecture has a size which is 13.5 times larger than that. So the trend says that sizes keep increasing. But this is a problem because register files are already huge and also power hungry. So a different approach to increase thread level parallelism to be to better utilize the register resources by decreasing the footprint of each thread instead. And that is the main objective of our register file. Our proposal builds upon two observations. The first one is that many applications can handle a much lower floating point precision than what they are currently using. Also, it's possible to tune the precision of all the floating point values offline in order to meet a certain quality threshold. As the quality threshold is lowered, and thus the precision, less information needs to be stored, and thus more threads can fit into the register file. The second observation is that it's possible to carry out a static analysis offline in order to find the range of each integer and thereby reduce the number of bits needed to store these integers. That also means that the footprint of the integer operands can be reduced, and thereby we can also increase the thread level parallelism. The problem, however, is to make use of both of these observations at the same time, because existing techniques for GPUs either rely on runtime detection of narrow integer values, and that doesn't work for floats, or it supports only statically detected narrow integers or precision-reduced narrow floats. So the problem we want to solve is how to design a register file which utilizes both narrow floats and narrow integers. The contribution of this paper is a new GPU register file organization which supports both narrow integer and float data. The register file is built upon a new concept for efficient packing of narrow operands, which is based on static bit width analysis co-designed with the new register file organization. We also present an evaluation of benefits, where we show up to 79% performance improvement, on average 18.6% improvement, when allowing for a slight quality loss in the output data. This is the outline for the rest of this presentation. I will start with describing our approach and the challenges connected to that approach. I will then give you a description of the proposed register file organization. Then I will show you the evaluation methodology together with our results, where I will focus on impact on register pressure and performance, as well as the overhead estimation before I conclude. This is an overview of our framework, where the blue part is carried out offline and the green part is carried out during execution. Let's first look at the offline part, where the input is the application code, a number of sample inputs, and a quality threshold. First, a range analysis is carried out to determine the bit width needed for each integer. Also, a precision tuning step is carried out, which sets the precision of each float value to meet the specified quality threshold. The output of these two steps are width annotations at instruction level, which are taken into account by the register allocator. Finally, the output is indirection information, which locates each operand within the register file. The precision tuning and register allocator were presented by us in a previous work and is published in TACO in December 2017. The range analysis we used was presented by Pereira, Rodriguez, and Campos in CGO 2013. During execution, the indirection info is used to find the operands in the register file. So let's look at this in more detail. Let's look at an example where we have two operands which are 8 and 24 bits in size. In the baseline, we would need two 32-bit physical registers in order to store these two operands, which of course wastes a lot of space. In our approach, we make two changes to the baseline. We slice the physical registers into 4-bit slices, and then we access these slices using the indirection table, which contains the indirection info from the previous slide. Each entry in the indirection table corresponds to an architectural register and points at the physical register, and the slices used are identified using an 8-bit mask. This way, both operands can fit into the same physical register, and we don't waste any space. It's also possible to split an operand into two parts and place these two parts into separate physical registers. Although it increases complexity, it also avoids fragmentation and enables a more space-efficient allocation. When it comes to low-precision floating point formats, we support a format which we proposed in a previous work. Normally, GPUs only support IEEE-compliant formats of 64, 32, and 16 bits. However, in previous work we saw that we could significantly decrease the number of bits used per operand by using a more fine-grained format. Because of that, our register file supports 7 different precisions, which are presented here. The ratio between the exponent and mantissa bits is roughly the same as in the IEEE-compliant format, but we use a more fine-grained format. This approach brings about a number of challenges. First, the indirection table is on the critical path, since a lookup has to be made before accessing the register file. Second, multiple of those accesses has to be carried out each cycle in order to not create a bottleneck. Third, conversions between floating point formats are necessary because we assume no changes are made to the execution units, and they do not support any other format than IEEE-compliant formats. Hence, floats stored in a low-precision format needs to be converted to 32-bit floats before and after execution. Before presenting our proposed register file organization, I will discuss how the baseline architecture works. In the baseline, the register file is divided into a number of banks, where each bank can be accessed once each clock cycle. And in order to access these efficiently, a structure called an operand collector is used. When an instruction comes from the dispatch units, it is allocated to one collector unit, and it remains there until all operands are collected. Each clock cycle, the collector unit can gather one operand, which means that an instruction might be in the collector unit for many cycles before it is released to the execution units. In order to maximize throughput, a structure called an arbitrator is distributing the requests from all of the collector units in such a way that the number of register bank accesses is maximized in each cycle. This structure is built for throughput over latency. This is our proposed register file organization, where the green blocks are new structures and the blue blocks are extended as compared to the baseline. During a read, the location of the operand is looked up in the source indirection table. This one is banked in the same manner as the register file itself in order to reach the same bandwidth as the register file, and this is to avoid bottlenecks. The location of the operand is fetched to the collector unit, which sends a request for that location to the arbitrator and register file. Then, a value extractor extracts the data from the slices and puts the slices together into a full value again. And this value is then returned to the collector unit. The last step is to convert the value to a 32-bit float if needed. That is, if it's a float which is of low precision. After that, the operand is again stored in the collector unit before the instruction is released to the execution units. During a write-back, a separate indirection table is used as to not create congestion on the critical path. This is an overview of the full operand collector pipeline, where the white stages are the original ones and the green stages are the one we have added. The source and destination indirection table are consulted for all operands and they take a cycle each. The value extractor is also consulted for all operands, but the logic is shallow and fast, so it fits into the same cycle as the register fetch. The value converter and truncator takes one cycle each, but they can be bypassed if the operand is an integer. In total, the pipeline is deeper than in the baseline, but these extra stages are hidden well, as we will see in the results section. We implemented our proposed register file organization in GPGPU Sim. We used 11 benchmarks. 4 of them are graphics benchmarks, which are selected because they include standard passes in many real-time graphics applications. We also use 7 kernels from the Rodinia benchmark suite, and these kernels were chosen because the register pressure is limiting the thread level parallelism in these kernels, and also they can be run on the simulator. We also use different quality metrics for these different benchmarks. For the graphic benchmarks, which produce images, we use structural similarity index, which is a method of comparing the quality of a reference image and the produced image. For the Rodinia benchmarks, which produce numerical outputs, we used the average relative error for most of them. But for one, which is a sorting algorithm, we used a binary quality metric, which only tells if the output is correct or not. Let's start by looking at how the framework impacts the register pressure. So on the y-axis, you have the register pressure, which is the maximum number of physical registers needed by a single thread. We show the original register pressure, the register pressure when only narrow integers are considered, and also when only narrow floats are considered. And we do this for 2 different quality thresholds, which we call perfect quality and high quality. Perfect quality means that the output does not deviate anything from the original output, while high quality means that it does not deviate more than maximum 10% from the original output. There are 2 main takeaways from this graph, and that is that the register pressure is lowered in all cases, and also that both integer and float reduction is important. For example, by looking at CFD and deferred, we can see that the floating point part of the framework heavily reduces the register pressure, but the integer part does not do much of a difference. On the other hand, if we look at DVT2D and the hotspot benchmarks, it's the other way around. So here, the integer part heavily reduces register pressure, but the floating point part does not. In summary, both of these parts are important to reach a significant reduction in register pressure. And that is true for both of the quality thresholds. Let's also look at the impact on performance, and this is for a very high quality threshold, which means that SSIM is no less than 0.9 and the average relative error is less than 10%. Also, for the binary quality metric, which is used for hybrid sort, all outputs are correct. On the y-axis, you can see the IPC, which is normalized to the baseline IPC. In the best case, we get a 79% improvement for the IMGVF kernel, and in the worst case, we get a reduction in between 5 to 9%, and this is because of contention in the texture cache. So when the number of threads is increasing, the pressure on the texture cache increases to a point where we get thrashing. Also, hotspot shows a decrease, and this is because of the deep pipeline we have. But note that we have a very conservative estimation of the write-back pipeline depth, and there is a sensitivity analysis of this in the paper. On average, we get an 18.6% increase in ICP. We have carried out an estimation of the area overhead using transistor count as a proxy for area. The estimation has been done through logic synthesis and also counting the number of transistors in standard cells, for example SRAM 6 transistor cells for each of the added structures. In total, we found that we add less than 1% of the total chip transistor budget for all the structures we add. We have also carried out an analytic estimation of the power overhead. When it comes to static power, the increase is linear with the circuit area. This means that the static power overhead is roughly the same as the increase in circuit area, hence a bit less than 1%. For dynamic power, our conclusion is that the overhead is less than the overhead would be if we would increase the size of the register file by 2x. This comparison is interesting because in some cases, we increase the number of threads by 2x, which would require a twice as large register file. The main reason for this conclusion is that the largest difference as compared to the baseline is that we occasionally do 2x fetches per operand. How often this happens is controlled by the compiler, since there is a trade-off between packing operands tightly and placing them in only one physical register. If we look at the worst case scenario, the 2x fetches would double the power. However, this does not happen each time. Hence, power is not doubled. If we instead would look at a twice as big register file with double as many entries, we would also need twice as long bit lines. Since most dynamic power in SRAM is due to bitline charging, we would need 2x more power for each fetch in the case of a twice as large register file. The bottom line is that the power expenditure is less than it would be for a twice as large register file. In conclusion, we present a new GPU register file organization which supports both in narrow integer and float data at the same time. It is based on a new concept for efficient packing of narrow operands. In addition, we also present an evaluation of benefits, which shows that the performance can be increased by up to 79%, 18.6% on average, when allowing for a slight quality loss in the output data. Also, this is while only using less than 1% of the total chip budget. That concludes this presentation. Thanks for watching.